Hello again. Here we'd like to talk about support reactions, in particular regarding a beam suspended at either end, which has a couple of loads placed upon it. Okay, so let me first of all draw this beam. Perhaps I could not have to scroll on the screen, would be useful. Let me try it anyway. Okay, do it in yellow. Here's the beam in question. Okay, not paying extra attention to neatness at the moment. There's a beam, wooden, metal, where it might be. We have the left side. We have a right side. I'm going to put some forces in now for you. Do these in white. We've got a reaction force on the left, basically something that's holding up the left side of the beam. On the other hand, it's not going to be held up very well unless we have something holding it up on the right hand side, which will obviously create another force upwards. Okay. Maybe we could have this beam, maybe for distance I can use pink here. Try to make the diagram clear as possible. How about an 8-meter beam? Total length. Okay. I think we could have exactly halfway as best as I can make it. We have a load on the beam of at the halfway point, 2 space lowercase k capital N, 2 kilonewtons. Okay, that is going to be at 4 meters, obviously, because it's halfway. And perhaps I could do another. It's not to scale, but as best as I can possibly achieve on this particular size of drawing. Maybe I could draw. I'll just draw a dotted line here. Dotted line there. I'm going to use that pink distance. So that distance there, I'm going to nominate that as, let me see, do it this way, 1.5 meters. Yep. And if that's halfway, that's the remainder of between 1.5 and 4 meters, which is clearly 2.5 meters. Okay, so we're going to have 2.5 meters here. So you add up your 1.5 meters and your 2.5 meters, and you get halfway along the beam. Okay. The thing I haven't added yet is this particular force at 1.5 meters. Let me do maybe 5 kilonewtons. Okay. So 5 kilonewtons force downwards, 1.5 meters from the left, a further 2 kilonewtons force, exactly halfway along the beam. Okay, and obviously we have some support reactions RL and RR, and basically our objective is to find out what these two guys are. That's our objective. Okay. Let's see if we can move over to the right and analyze this system now then. So what I'm going to do is I'm going to take moments about L, which is the left hand side. Okay, so when we say take a moment is essentially the product, or you're multiplying a distance times a force in what appears to be a rotational manner. Okay, so we take moments about L. I'm therefore going to be, maybe bullet point that one. Then what I'm going to do is I'm going to look at L here. I'm going to move to the right until I see a force, and I'm going to multiply that force by the distance moved. Okay, That's what we mean by a moment. So 5 kilonewtons force I see here. Okay, so I'm moving from left to right. 5 kilonewtons, put in the proper values then. So 5,000 times the distance I've moved so far is 1.5 meters. Okay, 1.5. Make the dot clear for the video. 5,000 times 1.5 plus, well, I move along and I see another force here, downward force, 2,000. Multiply that by the distance moved when you've negotiated that particular force. So in total, we've moved 4 meters, yeah, from the start until we hit that point, that force. Okay, so 2,000 times 4. That's all the downward forces. And if you like, we've got the left-hand side on a hinge, so we're looking at, that's what really you're doing when you're taking these moments, you hinge one side. So everything on the right-hand side's got to equal that lot on the left there, okay? So it's going to be the reactive force on the right, RR, times, well, what's the distance from our starting point, our hinge, all the way across to the right? Well, it's just the length of the beam, so it's 8. Okay? Therefore, we can say, well, we can add these, we can multiply these out and add them up. So we've got 1.5 times 5,000 gives us 7,500. 2,000 times 4 gives us 8,000 equals 8 lots of RR. Okay, 8,000 plus 7,500 is going to be equal to 15,500. Therefore, the reactive force on the right, RR, is got to be equal to 15,500 over 8, which is, well, maybe I could do it in a different colour to highlight it at the end. 1937.5. It's a force, so space capital N newtons. Okay, let's repeat the process, but this time we're going to hinge the right hand side and go the opposite way. So we're going to take moments about R. Okay, so we're starting here and we're moving that away. Okay, so when we do that from the right hand side, we have to travel, well, 4 meters before we hit 2 kilonewtons. Okay, so we're going to write, there's the 2 kilonewtons, multiplied by the distance moved from right to left until you hit that 2 kilonewton force. It's 4 meters. Get the idea? And then I'm going to add, the next thing I see is that 5 kilonewton force there. But its total distance is going to be halfway along here, this 4, plus this 2.5, which is 6.5. Okay, so therefore we're going to have 5,000 times 6.5, and that is going to be equal to the hinge end. Now at the moment, sorry, not the hinge end, the opposite of the hinge end. Hinge is here at the moment, and we're looking at this reactive element here, RL. Okay, so that's going to be equal to RL times 8. Keep the notation constant. Okay, so we have 2,000 times 4, again, 8,000. 6.5 times 5,000. I think it's 32,500. That's equal to 8 lots of RL, which is equal to 32,500 plus 8,000. 40,500. Okay. Therefore, we can say our L is equal to 40,500 divided by 8, which is equal to, be consistent and switch to pink now, 506 2.5 newtons. Okay, so just over 5 kilonewtons. You'll notice here that I'm not using any decimal places or anything. I want complete accuracy because I'm going to perform a check now. Okay, and I'll go over onto the left here. Maybe I can switch to yellow now for you. So let's perform a check. And basically our check is this: our upward forces equal our downward forces. Okay, so, or if you like, let's do it the other way, because we did the downward forces first. So downward forces must equal upward forces. And if that's not the case, then the beam is going to move either up or down, or possibly on a twist. Okay, so let's compute our downward forces first then. So we have 5 kilonewtons plus 2 kilonewtons. Maybe I could wrap these there and indicate a downward arrow common to both of those. Okay, so that's what we had in the question. We had 5 kilonewtons down, 2 kilonewtons down. I've just written them down here. They're downward forces. We're just checking that these things over here in pink are going to be correct. So those upward forces, so we have 1937.5 plus 506.5 and give that an up arrow. That's a common factor. Okay. And we add 5 plus 2 over on the left here. Clearly 7 kilonewtons up is balanced by this plus this is exactly 7. I like to cross my sevens. 7 kilon. Sorry, that direction was down, wasn't it? My mistake. Okay, so that's 7 kilonewtons down, and this one is 7 kilonewtons up. So our check is done, and therefore we've performed the calculations well. Okay, so that's how you undertake calculations for support reactions for beams. Hope that's been useful for you. Thanks for watching. See you next time.